All right, engineers, welcome back to The Explainer. Today we're diving headfirst into the system architecture of Osmantic ODS. Look, if you've been tracking the local AI space at all, you know it is incredibly fragmented right now, right? You're out there practically duct taping together model runners, chat front ends, and embedding services all by hand. But today, we're looking at a genuinely fascinating self-hosted local AI operating stack that is aiming to just solve all that in one fell swoop.
Which brings us to the big question. Is Osmantic ODS just another thin AI wrapper, or are we actually looking at the groundwork for the first true local AI operating system? To figure that out, we're going to do a comprehensive top-down architectural teardown. We'll evaluate its design patterns, its operational flow, and, super importantly, for anyone running this in production or a home lab, its security posture.
So here is our blueprint for today's audit. We'll hit 1. The AI appliance paradigm. 2. The provisioning pipeline. 3. Runtime and control plane. 4. Extensions and model management. And finally, 5. Security and engineering assessment. Let's get right into it.
Starting things off with Section 1, the AI appliance paradigm. To get the big picture here, ODS isn't just a UI. It actually bundles inference, RAG, agents, and workflows into a complete, containerized environment purpose-built for local hardware. Look at how it elegantly maps out these three core layers. Notice how it completely separates hardware provisioning, which is driven by shell scripts and installers, away from the containerized AI execution in the runtime layer, which is heavily Docker and Python-based. And then, sitting on top, you have the control plane, managed via a CLI and a JavaScript dashboard. Honestly, this separation of concerns is a classic, robust design pattern. It's a huge hint that we are dealing with way more than just a weekend project here.
Moving right along to Section 2, the provisioning pipeline.
From a systems engineering perspective, the ODS installer is the absolute beating heart of the system. It does far, far more than your typical Docker Compose setup. When you spin this thing up, it doesn't just pull containers. First, it detects your specific hardware. Then it hits a service registry, moves through highly ordered installation phases, routes through platform-specific paths, whether you're on Mac, Windows, or Linux, and finally triggers its model selection logic. It's dynamically building your AI environment based on the exact specs of your host machine.
I mean, we've all been there with the traditional setup, right? Losing hours at 2 a.m. manually trying to figure out the right quantization, tweaking context lengths, selecting a specific backend, and just agonizing over hand-tuned GPU flags to stop the container from constantly crashing. ODS saves you from that absolute nightmare by seamlessly abstracting everything into automated hardware tier mappings. It just knows your hardware and it configures the stack to match. A total lifesaver.
All right, into Section 3, runtime and control plane.
So once that provisioning is completely done and the hardware is mapped out, we transition into the service-oriented runtime, where the actual magic happens. Let's trace the request lifecycle for a second. Take a simple command like, summarize my PDF. The request flows downwards so elegantly. It enters through the user interface, hits the control plane, which is acting as the operational brain of the whole thing, routes into the runtime services, specifically firing up the RAG and inference containers, and finally hits that hardware abstraction layer to execute directly on your local silicon. It is a super clean, microservice-like lifecycle, all happening entirely locally on your machine.
Next up, Section 4, extensions and model management.
Now, any robust architecture needs to be adaptable, right? And one of their strongest architectural choices is this extension model. They use what's called an extension manifest. Basically, this is a configuration file that dictates how a completely new modular AI service, say you want to drop in a new voice generation tool or some bleeding-edge agent framework, gets dynamically merged into your active stack via a Docker Compose fragment. You don't have to tear down the entire system just to add one new tool. It just slots right in.
As an engineer, you'll instantly recognize this pattern. This is highly analogous to Kubernetes operators, Home Assistant integrations, or even VS Code extensions. It takes what could be a static, rigid deployment and turns it into a highly extensible, plug-and-play local ecosystem. It is a really smart architectural move that guarantees the platform can actually keep pace with the incredibly fast-moving open-source AI community. Similarly, we've got the model management subsystem. Instead of making users manually download gigabytes of GGUF or SafeTensor files and painfully wiring up rigid file paths, the model manager acts almost like a hardware-aware AI scheduler. It handles what models are available, it manages the downloads, allows for seamless switching, and even handles rollbacks automatically. It completely hides all that underlying complexity from the end user. Okay, bringing it home with Section 5, Security and Engineering Assessment.
Now, if we're going to hand a system this much control over our hardware and our private data, we need to know exactly where the weak points are. A quick glance at the repository breakdown reveals something fascinating and, well, maybe a bit concerning depending on your background. We're looking at a massive footprint of shell scripts, literally 45% of the codebase driving the installer and orchestration layer, with Python and JavaScript making up the bulk of the rest.
Let's be real. We all know that existential dread of reviewing a codebase that is heavily reliant on shell scripting. Having a 40% plus shell repository introduces some very serious engineering concerns. It creates a massive surface area for edge cases. You've got quoting bugs, privilege escalation mistakes, cross-platform portability issues. Shell is incredibly powerful for bootstrapping, absolutely, but it can be really brittle as a complex orchestrator.
And this leads us directly to a really critical question. Where do the trust boundaries actually sit in a unified local AI appliance like this? Because the installer is acting as a highly privileged supply chain component. It's detecting hardware, it's managing Docker sockets, it's downloading external binaries. We have to be hyper-aware of where the network and privilege boundaries are actually drawn.
So if you're running this stack, you absolutely must actively defend against container escapes. That means never, ever running these containers as privileged unless it's absolutely necessary and you need to heavily audit Docker socket access. Second, data leakage. Your private RAG data and your embeddings, those are just as sensitive as your company's proprietary source code, and they need that exact same level of protection. Finally, the model supply chain. We really need a paradigm shift here. Downloaded models are not just static text files anymore. They are essentially executable data, which requires strict verification and version pinning.
Beyond the security aspect, we also have to talk about scalability limits. ODS relies heavily on Docker Compose. And look, while Compose is absolutely fantastic for single-node home labs and dev environments, it becomes a distinct architectural bottleneck if you ever attempt to scale ODS into multi-node deployments, or if you need rolling zero-downtime upgrades, robust service discovery, or true high availability. Right now, it is very much a single-machine appliance.
So where does all this leave us? Well, here is our final audit. Despite those orchestration limitations and the arguably heavy reliance on shell scripts, ODS is still a massive leap forward. It is effectively acting as a powerful Proxmox or Docker appliance specifically for local AI. It drastically reduces the complexity of assembling a private AI ecosystem and directly solves the messy, duct-tape fragmentation of local deployments that is plaguing engineers right now.
I'll leave you with this final thought to chew on today. As our local AI stacks grow more and more complex, integrating agents, RAG, multimodal inference, will Docker Compose survive as the bedrock? Or, looking at the abstractions that ODS is building right now, are we simply watching the messy birth of a totally new kind of distributed AI orchestration layer? Like, are we looking at an AI Kubernetes? Think about it. Thanks for joining me on this Explainer, engineers. Take this architecture, audit it yourself, and keep building.